The planet beneath our feet feels solid, predictable, alive. Oceans breathe in steady rhythms. Forests rise and fall with the seasons. The sky, unchanged within a human lifetime, gives the illusion of permanence. But this calm is deceptive, because the Earth you know, the one that feels ancient and enduring, is not the first version of this world. It is not even the second, or the third, or the fourth. It is the sixth draft. 5 times before, life on this planet was almost completely erased, not wounded, not diminished, but driven to the edge of annihilation. Oceans emptied of complexity, continents stripped of ecosystems, the evolutionary clock violently reset. And yet, life returned, altered, rewritten, transformed. This is not a story about extinction as an ending. It is a story about extinction as a force of creation, about collapse as a crucible, and about a haunting question that echoes through deep time. If intelligence emerges from catastrophe, does it ever learn from it? To answer that, we must travel backward, far beyond memory, beyond history, to a time before the first ending, when Earth was young and life believed it had forever, and did not yet know how wrong it was. The Earth was not born gentle. It began in violence 4.5 billion years ago as a glowing sphere of molten rock assembled from cosmic debris left behind by the formation of the Sun. Asteroids collided, planetesimals shattered, heat from radioactive decay and gravitational compression turned the young planet into an ocean of magma. There was no sky as we would recognize it, no oceans, no life, only fire, impact, and time. Then, slowly, almost imperceptibly, the planet cooled. A crust formed, thin and fragile at first, repeatedly broken and remade. Water arrived, delivered in part by icy bodies from the outer solar system and in part released from Earth's own interior. Rain fell for thousands of years without stopping, filling basins, carving the first scars into rock, creating the oceans that would become the great engine of life. Above them, an atmosphere thick with carbon dioxide, methane, ammonia, and water vapor wrapped the planet in a dense, choking shroud. There was no oxygen to breathe. For any modern organism, this world would have been instantly lethal. And yet, it was here, within this hostile chemistry, that life began. The earliest living systems were simple beyond imagination. Single-celled organisms, likely resembling modern bacteria and archaea, emerged more than 3.5 billion years ago. They did not see. They did not think. They did not move with intention. They existed as chemical processes capable of copying themselves, harvesting energy from their surroundings, and persisting long enough to do it again. Earth, at this stage, was a microbial planet. Life did not walk or swim or crawl. It coated rocks. It drifted in water. It altered chemistry molecule by molecule. For nearly 2 billion years, nothing else existed. These microbial worlds were not static. Evolution was already at work, refining metabolisms, diversifying survival strategies. Some organisms learned to extract energy from sulfur, others from iron. And then, one lineage discovered something revolutionary: photosynthesis. Cyanobacteria began using sunlight to split water molecules, releasing oxygen as waste. At first, oxygen was poison. It reacted violently with dissolved iron in the oceans, rusting the planet from within. Vast bands of iron oxide settled onto the seafloor, forming geological records that still exist today. Only after the oceans could absorb no more did oxygen begin to accumulate in the atmosphere. This transformation, the Great Oxygenation Event, was the first global ecological catastrophe triggered by life itself. Entire anaerobic ecosystems collapsed. Countless organisms vanished. But the planet did not die. It changed. Oxygen opened the door to more efficient energy use, to larger cells, to complexity. Over time, eukaryotic cells emerged, cells with nuclei, internal structures, and the capacity to form multicellular organisms. Life learned to cooperate with itself. Bodies became possible, And then, around 541 million years ago, something extraordinary happened. In a geological blink of an eye, the Cambrian explosion transformed Earth into a world of visible life. Complex organisms proliferated in the oceans, creatures with shells, spines, eyes, limbs, and nervous systems. Trilobites scuttled across the seafloor, their segmented bodies armored like living machines. Brachiopods filtered nutrients from the water, anchoring themselves in vast colonies. Early chordates, primitive relatives of all future vertebrates, began experimenting with internal support structures, laying the groundwork for spines, skulls, and eventually intelligence. The seas were alive with forms that seem alien even now. Predators emerged. Vision reshaped survival. Arms races began, not between nations but between species locked in evolutionary competition. This was not a peaceful Eden, it was a dynamic, often brutal world, but it was productive. Biodiversity soared, ecosystems layered themselves with increasing sophistication. From a distance, Earth appeared stable. That appearance, however, is deceptive. Extinction is not an anomaly in Earth's history, it is a constant. At any given moment, species are disappearing. This is known as background extinction, the slow, continuous turnover of life caused by competition, environmental change, and chance. Species arise, species vanish. Over millions of years, this quiet process reshapes ecosystems without shattering them. It is the steady heartbeat of evolution. Mass extinction is something else entirely. A mass extinction is not simply an increase in deaths. It is a systemic failure of the biosphere. A collapse so rapid and so widespread that entire branches of the tree of life are severed at once. In scientific terms, it is defined by the loss of at least 75% of species across the globe within a geologically short interval, often less than a few million years, sometimes far less. What makes mass extinctions unique is not just how many species die, but how the rules of survival change. Traits that once ensured dominance become liabilities. Ecosystems unravel faster than evolution can adapt. Food webs collapse from the bottom up and the top down simultaneously. Recovery, when it comes, takes millions of years and produces a world fundamentally unlike the one that came before. Crucially, mass extinctions do not require malice. They do not require intention. They can be triggered by forces entirely indifferent to life. Shifts in climate, changes in ocean chemistry, tectonic upheaval, volcanic outpourings, or astronomical events. The planet itself becomes hostile, not in one place but everywhere. And this is the unsettling truth hidden beneath Earth's long, calm periods. Stability is not the default state. It is a temporary condition maintained by delicate balances. By the late Ordovician period, roughly 450 million years ago, Earth had settled into what looked like a thriving equilibrium. The continents were arranged differently, clustered mostly in the southern hemisphere. Sea levels were high, flooding continental shelves and creating vast, shallow marine habitats, the most productive ecosystems of the time. Life flourished almost entirely in the oceans. There were no forests on land, no animals walking the surface. The seas belonged to invertebrates, trilobites, brachiopods, mollusks, corals, and countless forms now long extinct. Climate, for millions of years, had been warm and relatively stable. But stability can mask tension. Atmospheric carbon dioxide levels began to fall, whether driven by increased weathering of rocks, shifts in ocean circulation, or biological feedbacks. The planet's thermostat started to turn. Temperatures dropped. Ice sheets formed on the southern supercontinent of Gondwana. Glaciers advanced silently, locking away enormous volumes of water. Sea levels began to fall. For organisms living in shallow seas, organisms that made up the majority of Earth's biodiversity, habitat vanished not gradually, but catastrophically. Entire ecosystems were stranded, compressed, or destroyed. And when the climate swung again, warming rapidly as ice melted, conditions did not return to normal. The oceans became unstable, oxygen levels fluctuated, and species already stressed by loss of habitat were pushed past their limits. The world was about to learn its first great lesson in extinction. There was no asteroid in the sky, no volcanic apocalypse blotting out the sun, no external villain, just climate, slowly shifting, then suddenly unforgiving. This is the first warning written into Earth's history. Catastrophe does not always announce itself with fire. Sometimes it arrives as ice, and with it comes the first collapse. The first mass extinction did not come from space, but from ice. The collapse begins quietly, not with an explosion, not with darkness at noon, but with a cooling breeze that does not stop. Around 444 million years ago, at the boundary between the Ordovician and Silurian periods, Earth crosses an invisible threshold. For millions of years prior, the planet had existed in a warm greenhouse state. Carbon dioxide concentrations were high, polar regions were largely ice-free, sea levels were elevated, flooding continental margins and creating vast shallow seas, the biological engines of the ancient world. Then the balance shifts. Geologically speaking, the transition is abrupt. Within a span measured not in tens of millions of years, but in a few 100,000, perhaps even less, global temperatures fall sharply. Carbon dioxide levels drop, likely driven by increased weathering of newly exposed land and long-term tectonic processes that quietly siphon greenhouse gases from the atmosphere. The planet's thermostat is turned down, and once it begins to fall, feedback loops accelerate the descent. Ice forms where none had existed before. The southern supercontinent Gondwana drifts over the South Pole, and massive ice sheets begin to spread across it. Glaciers advance outward, kilometer by kilometer, locking away unimaginable volumes of water. As they grow, sea levels fall, first slowly, then dramatically. Estimates suggest a global drop of tens of meters, perhaps more. For a planet whose life is concentrated almost entirely in shallow oceans, this is not a minor adjustment, it is an existential shock. The seas retreat from the continents. Vast continental shelves, the nurseries of marine life, are exposed, drained, erased. Ecosystems that had persisted for tens of millions of years are destroyed not by predators or competition, but by simple absence. Water is gone, habitat is gone, temperature gradients sharpen, nutrient flows collapse. What remains is a fragmented ocean, colder, shallower, and increasingly hostile. The victims are everywhere. Trilobites, once among the most successful animals on Earth, begin to vanish in staggering numbers. Entire families disappear. Brachiopods, bryozoans, corals, graptolites, organisms that had defined Ordovician seas, collapse in waves. Reef systems disintegrate. Food webs unravel from their foundations. By the height of the crisis, roughly 85% of all marine species are gone. This is Earth's first mass extinction. It is important to understand the speed. In human terms, this is slow, unimaginably slow, but in geological terms, it is violent. Evolution cannot pivot fast enough. Adaptation requires generations, and generations require stability. Here, stability has evaporated, and yet, extinction does not arrive as a single blow. As the Ice Age peaks, conditions remain brutal. Cold waters hold more oxygen, but the problem is not oxygen alone. Temperature swings intensify, seasonal extremes worsen. Many organisms adapted to narrow ecological niches, warm, shallow, sunlit seas, have nowhere to go. Then, just as abruptly, the planet changes again. The ice begins to melt. Carbon dioxide levels rise, perhaps released by volcanic outgassing, or reduced weathering as glaciers retreat. Sea levels surge back. Shallow seas return to the continents, flooding landscapes that had been dry for hundreds of thousands of years. On the surface, it looks like recovery, but the returning oceans are unstable. Rapid warming stresses survivors already weakened by cold. Oxygen levels fluctuate. Stratification increases. Chemical conditions shift faster than ecosystems can reorganize. This second phase of the extinction delivers another blow, eliminating species that survive the ice only to succumb to heat and chaos. The extinction comes in pulses: cold, then warm, retreat, then flood. What makes this event particularly revealing is that there is no single culprit, no asteroid crater, no obvious scar in the rock that announces catastrophe. Instead, the Ordovician to Silurian extinction demonstrates something far more unsettling. Climate alone, when pushed beyond a threshold, is sufficient to nearly sterilize a planet. And yet, life does not vanish entirely. Some organisms endure. The survivors are not the largest, nor the most elaborate, nor the most dominant of their time. They are the flexible ones, species with broader temperature tolerances, organisms capable of living in deeper waters where conditions change more slowly, lineages with generalized feeding strategies rather than specialized diets, populations scattered across wide geographic ranges rather than concentrated in a single ecological sweet spot. Refugia matter. Deep ocean basins, less affected by sea level change, become sanctuaries. Certain planktonic organisms persist by sheer abundance and rapid reproduction. Some benthic species survive by burrowing into sediments, riding out environmental extremes beneath the surface. The lesson is clear, though no one is there to learn it. In moments of planetary crisis, dominance is a disadvantage. Specialization becomes fragility. The traits that define success in stable times, efficiency, optimization, ecological supremacy, turn lethal when conditions swing too far too fast. Extinction, it seems, does not reward the best adapted to yesterday's world. It selects for those most capable of enduring tomorrow's uncertainty. As the climate stabilizes and the Silurian period begins, life slowly rebounds. Seas reclaim the continents. Ecosystems reassemble, not as they were, but as something new. Biodiversity rises again, though the cast of characters has changed. Entire evolutionary pathways have been closed forever. Others, once minor, now expand into the vacant spaces left behind. The planet looks alive again, but it is not the same planet. The Ordovician to Silurian extinction leaves behind a biosphere permanently altered, a reminder etched into stone that Earth's systems are not fixed. They oscillate. And with each oscillation, life is tested. The oceans refill. Life returns. But beneath the surface, new dangers are already taking shape. The ice retreats, and the planet exhales. In the wake of the first mass extinction, Earth enters a long, uneasy recovery. The Silurian period opens on a world that is quieter than before, its oceans less crowded, its ecosystems stripped back to simpler frameworks. But absence creates opportunity. With competitors erased and niches left vacant, life begins again, not as a return, but as a reinvention. The seas stabilize first. As global temperatures even out, shallow marine environments re-establish themselves across flooded continental margins. Sunlight once again penetrates broad shelves of warm water, and with it comes productivity. Coral reefs reappear, not the same reefs that vanished during the Ordovician collapse, but new constructions built by survivors and opportunists. These reefs become engines of diversity, assembling complex food webs from the rubble of extinction. Fish begin to change. Early jawless fish, once marginal, diversify rapidly. Some lineages experiment with armor, bony plates that turn bodies into living fortresses. Others develop jaws, transforming feeding from passive filtering into active predation. This innovation alters everything. With jaws comes specialization. With specialization comes escalation. Predator and prey evolve in tandem, locked in cycles of adaptation that accelerate evolutionary pace. Below the waves, complexity is returning. But above them, something unprecedented is beginning. For most of Earth's history, land has been a hostile frontier. barren rock, blasted by ultraviolet radiation, scoured by wind, devoid of soil. Life clings to the margins, microbial mats along shorelines, thin films of algae on damp surfaces. Now, during the Silurian and early Devonian, plants begin a slow, momentous invasion. At first they are small. Simple, rootless organisms creep across moist ground, anchoring themselves with thread-like structures. They lack leaves, lack height, lack any obvious grandeur. And yet, their impact is revolutionary. These early plants stabilize soil. They trap sediments, they hold water. For the first time, the land is no longer just rock. It becomes an ecosystem in waiting. As plants spread, the planet itself begins to change. Roots pry into stone, accelerating chemical weathering. Minerals once locked safely in bedrock are broken free and carried by rivers into the oceans. Nutrients, phosphorus, nitrogen, trace metals, flow downstream in growing quantities. At the same time, plants draw carbon dioxide from the atmosphere through photosynthesis, locking it away in organic matter. The air slowly transforms. Carbon dioxide levels decline. Oxygen rises. Climate responds. What appears on the surface to be a triumph of life is also the beginning of a new instability. The greening of the continents alters erosion rates, river chemistry, and atmospheric composition on a global scale. Earth systems, once governed largely by geology, are now being reshaped by biology. Life is no longer just adapting to the planet, it is engineering it. During the early Devonian, this transformation accelerates. Plants grow taller, vascular tissues evolve, allowing water and nutrients to be transported upward against gravity. True roots anchor vegetation deeper into the soil, intensifying weathering processes. Primitive forests begin to form, sparse at first but spreading. In the oceans, the consequences are subtle, then profound. Nutrient influx fuels explosive growth of algae and plankton. Productivity surges, but productivity has a dark side. As blooms die and sink, bacteria consume them, using up dissolved oxygen in the process. Vast regions of the seafloor begin to suffocate. Oxygen-poor zones expand, creeping upward through the water column. Anoxia returns. This time, it is not driven by ice or by sudden catastrophe, but by success. Life has become so efficient at reshaping its environment that it begins to undermine the conditions it depends upon. The warning signs are scattered and slow. Reef systems struggle in places. Certain marine species show stress. Biodiversity fluctuates, but nothing yet resembles a mass extinction. From the perspective of the moment, the world looks vibrant, inventive, full of promise. And indeed it is. This is a golden age of experimentation. Arthropods venture onto land. Early tetrapod ancestors lurk in shallow waters, their fins slowly adapting to weight and air. Ecosystems become layered, interconnected, increasingly complex. Evolution seems to be accelerating, not stalling. But complexity carries risk. As systems grow more intricate, they also grow more sensitive. Feedback loops tighten. Small changes ripple farther. The margin for error shrinks. The planet is quietly storing tension. Carbon is being buried at unprecedented rates. Atmospheric composition is drifting. Ocean chemistry is shifting toward instability. Nutrients continue to pour from the land into the seas, year after year, century after century, millennium after millennium. No single organism intends this outcome. There is no foresight, no design, just cumulative consequence. And this is the deeper pattern emerging from Earth's history. Mass extinctions are not always interruptions from outside. Sometimes they are the unintended results of life's own innovations. Progress creates pressure. Success reshapes the rules. The world once again appears stable. But beneath the surface, the conditions for collapse are assembling slowly, patiently, as they always do. Because the rise of plants, this quiet conquest of stone and soil, will not merely change the land. In time, it will destabilize the oceans themselves. And when that happens, The next extinction will not arrive suddenly. It will seep. If you are finding value in this journey through deep time, if these forgotten chapters of Earth's history are reshaping how you see the world beneath your feet, consider subscribing now. This story is only beginning, and what comes next will be far more dangerous than ice. Because the rise of forests will poison the seas. Extinction does not always arrive as a single moment. Sometimes it stretches itself across millions of years, creeping forward so slowly that life does not recognize the danger until escape is no longer possible. The Late Devonian extinction is not a sharp blade, it is a long suffocation, a drawn-out unraveling of the world, played out in pulses of stress, collapse, partial recovery, and deeper collapse again. It begins around 372 million years ago, but it does not end cleanly. For more than 10 million years, the biosphere is caught in a state of instability. Ecosystems fail, reassemble, and fail again. From the perspective of deep time, this is not one extinction, but a sequence of blows that together reshape life beyond recognition. To understand why this extinction is so prolonged, one must look not to a single cause, but to a convergence of forces, each reinforcing the other. By the Late Devonian, the planet has been fundamentally transformed by life on land. Forests are no longer experimental outposts. They are spreading, deep-rooted, and structurally complex. Tall trees dominate floodplains. Vast root systems fracture bedrock and accelerate chemical weathering at scales never seen before. Rivers carry unprecedented loads of nutrients into the oceans. Phosphorus, nitrogen, iron. The seas respond with abundance. Phytoplankton bloom explosively. Algae flourish. At first, this productivity seems beneficial. More life, more food, more energy moving through the system. But productivity without balance is dangerous. When these blooms die, their remains sink into deeper waters where bacteria consume them, and bacteria breathe oxygen. Slowly, relentlessly, oxygen disappears. Large regions of the oceans slip into anoxia, conditions so depleted of oxygen that most complex life cannot survive. In some areas, the situation worsens further. Hydrogen sulfide begins to accumulate, turning waters toxic. These are not localized dead zones. They are continental in scale, spreading across shallow seas that once supported the most diverse ecosystems on Earth. Reef systems are among the first casualties. Devonian reefs are immense, larger than anything before them. Built by corals, stromatoporoids, and microbial communities, they form the structural backbone of marine biodiversity. But reefs require stable conditions, clear water, consistent temperatures, sufficient oxygen. Anoxia shatters that stability. Reef builders suffocate, skeletons dissolve, entire reef complexes collapse, removing the foundation upon which thousands of species depend. Once reefs fall, the extinction accelerates. Armored fish, the placoderms, begin to disappear. These are the giants of Devonian seas, apex predators encased in bony plates. For millions of years, they dominated marine food webs. But dominance is not immunity. Large bodies require stable oxygen levels and reliable food chains. As ecosystems fragment, these giants become liabilities. One by one, entire lineages vanish. Climate instability compounds the crisis. The Late Devonian is marked by repeated swings between warming and cooling. As plants draw carbon dioxide from the atmosphere and bury it in sediments, global temperatures drop. Evidence suggests the onset of glacial conditions, even as greenhouse intervals punctuate the timeline. These oscillations place organisms under constant stress. Adaptations that work in one phase fail in the next. Oxygen levels in the atmosphere fluctuate as well. While oxygen had risen dramatically earlier in the Devonian, instability now sets in. For both marine and terrestrial organisms, respiration becomes more challenging. Combined with warming seas, which hold less dissolved oxygen, the result is physiological collapse across vast regions. Volcanism may have added fuel to the fire. Large igneous provinces are not as clearly defined here as in later extinctions, but episodic volcanic activity likely injected carbon dioxide and sulfur compounds into the atmosphere. These emissions would have driven short-term warming, acid rain, and further chemical disruption of oceans and soils. Volcanic ash may also have delivered additional nutrients to marine systems, intensifying eutrophication and anoxia. Some researchers have proposed even more distant triggers. Cosmic radiation events, such as nearby supernovae, have been suggested as contributors, potentially damaging the ozone layer and increasing ultraviolet radiation at Earth's surface. While debated, such hypotheses underscore the complexity of this extinction. No single smoking gun exists. Instead, the Late Devonian appears to be a cascading failure, a biosphere overwhelmed by the consequences of its own expansion, nudged further by geological and possibly astronomical forces. What makes this extinction particularly devastating is its selectivity. Not all life dies, but the patterns of survival are stark. Marine organisms tied to reefs suffer catastrophic losses. Species dependent on narrow oxygen ranges disappear. Large, specialized predators collapse first, followed by their prey. In contrast, organisms with flexible metabolisms, smaller body sizes, or tolerance for low oxygen conditions fare better. Freshwater ecosystems become unexpected sanctuaries. Rivers, lakes, and floodplains are less affected by widespread oceanic anoxia. Fish adapted to variable oxygen levels persist here, shielded from the worst marine collapses. These refugees allow certain lineages to survive when open oceans become hostile. And then there are the pioneers at the boundary between water and land. Early tetrapod ancestors, creatures still tied to aquatic environments but capable of brief excursions onto land, gain an accidental advantage. Shallow, oxygen-poor waters push them toward air breathing. Limbs, once useful for maneuvering in vegetation-choked swamps, become tools for escape. Lungs supplement gills. The shoreline becomes a lifeline. This is not a triumph. It is a necessity. Life does not leave the oceans because land is safer. It leaves because the seas are becoming uninhabitable. By the end of the Late Devonian extinction, an estimated 70 to 80% of species are gone. Entire ecological architectures have collapsed. Reef systems will not fully recover for tens of millions of years. The age of armored fish ends. Marine dominance shifts permanently, and yet something crucial survives. The blueprint for terrestrial life remains intact. Plants continue to diversify. Insects persist. Tetrapods carry the legacy of fish onto land, setting the stage for amphibians, reptiles, mammals, and eventually intelligence itself. The extinction prunes the tree of life brutally, but it also redirects its growth. This is the deeper truth revealed by the Late Devonian. Extinction does not merely remove life, it redirects evolution's trajectory. By destabilizing one realm, it forces expansion into another. The oceans, once the cradle of complexity, become a threat. So life begins to hedge its bets. It spreads upward, outward onto soil and stone. It experiments with air, with gravity, with exposure. The risks are immense, but remaining in the seas is no longer viable. The slow death of the Devonian oceans becomes the quiet birth of a terrestrial future. Life escapes the water and walks into danger. The land is no longer an experiment. By the dawn of the Carboniferous period, life has committed itself to the surface of the planet. What began as tentative excursions during the Devonian becomes a full occupation. Forests spread across the continents, not as scattered stands, but as vast, interconnected systems, dense, humid, and alive with motion. This is a world transformed by vegetation. Towering lycopsids rise like pillars, their trunks straight and scaled, stretching toward a sky richer in oxygen than at any other point in Earth's history. Ferns unfurl beneath them, horsetails crowd the wetlands, Roots knit the soil together, locking carbon underground in staggering quantities. Swamps thicken, peat accumulates, entire landscapes become engines for carbon burial, and the atmosphere responds. Oxygen levels climb, far beyond modern values. Estimates suggest concentrations approaching 35% compared to today's 21%. The consequences are immediate and dramatic. Fires burn hotter, metabolism becomes easier, respiration grows efficient, and insects grow enormous. Dragonfly-like creatures with wingspans wider than a hawk patrol the forest air. Millipedes stretch longer than a human arm, their segmented bodies gliding across the forest floor. Arthropods, freed from respiratory constraints by oxygen-rich air, expand into forms that seem impossible by modern standards. But this is not merely an age of giants, it is an age of transition. Amphibians thrive in the swampy lowlands, their lives still tethered to water. But alongside them, a quieter revolution is underway. Reptiles emerge, animals that break free from the final dependency on water for reproduction. The amniotic egg, sealed and self-contained, allows embryos to develop on dry land. This single innovation reshapes the future of life. Reptiles spread outward into drier environments, into interiors amphibians cannot reach. They diversify into forms both small and formidable, experimenting with posture, metabolism, and diet. For the first time, life truly claims the continents. Climate, for a time, cooperates. The Carboniferous world is warm but relatively stable. Ice caps wax and wane at the poles, but the planet maintains a delicate balance. Sea levels fluctuate, flooding and draining coastal forests, locking even more carbon into sediments that will one day become coal. These buried forests draw down atmospheric carbon dioxide, reinforcing cooler conditions and stabilizing climate, at least temporarily. This is a moment of apparent equilibrium, but stability on Earth is never permanent. As the Carboniferous gives way to the early Permian, the continents begin to converge. Plate tectonics, relentless and slow, draw land masses together into a single colossal supercontinent, Pangaea. Stretching nearly pole to pole, it reshapes the planet's geography on a scale unmatched before or since, and geography controls climate. As oceans are displaced, currents reroute. Warm equatorial waters no longer circulate as freely. Interior regions of Pangaea drift far from moderating coastal influences. Vast areas become arid, subject to temperature extremes, scorching heat by day, bitter cold by night. Seasonal contrasts sharpen. Monsoons intensify along the coasts, while deserts spread inland. Life adapts, but at a cost. Forests retreat from drying interiors, wetlands shrink, amphibians decline, constrained by moisture. Reptiles more tolerant of aridity expand their reach. The balance of power shifts again. Beneath the surface, deeper forces are stirring. The collision and stretching of tectonic plates generates immense stress in Earth's crust. In what will one day be Siberia, magma accumulates silently, pooling beneath the lithosphere. For now, it remains trapped, but the pressure is building. The planet's interior is preparing for release. Above ground, ecosystems appear robust, but cracks are forming. Carbon dioxide levels, once suppressed by rampant plant growth, begin to fluctuate. Oxygen peaks and then wavers. Fire becomes both a creative and destructive force, reshaping landscapes with increasing frequency. The very oxygen that fueled gigantism now makes ecosystems more flammable, more volatile. Life has built a complex, interdependent world. And complexity, once again, is a risk. The early Permian continues this uneasy equilibrium. Reptiles diversify into multiple lineages, some ancestral to mammals, others to reptiles and dinosaurs yet to come. Food webs grow intricate. Predators and prey refine their strategies. On land, ecosystems rival the oceans in diversity and productivity. But the oceans themselves are changing. As Pangaea restricts circulation, stagnant waters expand. Oxygen distribution becomes uneven. Chemical stratification increases. The conditions that once poisoned Devonian seas are quietly reassembling. though not yet at catastrophic scale. Earth has entered a phase of tension. The Carboniferous dream, a world of lush forests, soaring insects, and oxygen-rich air, fades into memory. In its place stands a harsher planet, one shaped by extremes, where survival favors resilience over abundance. Still, no one living could know what is coming. There is no warning written in the sky, no sudden collapse, only subtle signals, warming trends, chemical shifts, tectonic murmurs beneath the crust. The biosphere continues, unaware that it is approaching the most devastating event in its history. 5 mass extinctions will shape life on Earth. 4 have not yet occurred. But the greatest of them all is already assembling its forces, deep underground, beyond sight, beyond sound. The Earth is about to burn. The end does not come suddenly. It builds. By the late Permian, Earth is already strained, a planet locked into extremes. Pangaea dominates the surface, stretching from pole to pole, its vast interior isolated from oceanic moderation. Deserts sprawl, seasons swing violently, oceans circulate sluggishly, life persists, but the margins for error have narrowed to almost nothing. Then the planet breaks. Around 252 million years ago, in what is now Siberia, the Earth's crust ruptures on a scale without precedent. For hundreds of thousands of years, perhaps longer, magma floods upward from deep within the mantle, not as a single eruption, but as a sustained outpouring. Lava does not form a mountain, it forms a continent of fire. The Siberian traps are born. Basalt spills across millions of square kilometers, layer upon layer, burying landscapes beneath kilometers of volcanic rock. But the lava itself is only part of the catastrophe. As magma intrudes into coal beds, limestone, and organic-rich sediments, it triggers a chemical nightmare. Carbon dioxide, methane, sulfur dioxide, and halogen gases are released in staggering quantities. The atmosphere begins to change almost immediately. Carbon dioxide concentrations skyrocket. Methane, far more potent as a greenhouse gas, amplifies the effect. Global temperatures rise sharply, not by 1 or 2 degrees, but by 5, 8, perhaps more. The planet enters a state of runaway warming. Polar ice, already limited, disappears entirely. Tropical regions become lethally hot, but heat is only the beginning. Sulfur dioxide injected into the atmosphere reacts with water vapor to form sulfuric acid. Acid rain falls across continents, stripping leaves from plants, acidifying soils, poisoning fresh water systems. Forests weaken and die, reducing the planet's ability to absorb carbon and accelerating the feedback loop. Earth's climate system spirals. Warmer oceans hold less oxygen. Stratification increases as hot surface waters refuse to mix with cooler depths. Oxygen depletion spreads downward through the water column. Entire marine basins slip into anoxia, conditions incapable of supporting most complex life. Then comes the poison. In oxygen-starved seas, anaerobic bacteria flourish. These microbes metabolize sulfur compounds and release hydrogen sulfide, a gas toxic to nearly all multicellular organisms. The gas accumulates in deep waters, then rises, belching into surface layers and possibly into the atmosphere itself. Hydrogen sulfide does more than suffocate life. It attacks the ozone layer. As ozone thins, ultraviolet radiation floods the surface. Plants burn under unfiltered sunlight. Spores show signs of radiation damage preserved in the fossil record. The sky itself becomes hostile. Ocean acidification compounds the crisis. As carbon dioxide dissolves into seawater, it forms carbonic acid. pH levels drop. Calcium carbonate structures, shells, skeletons, reefs, begin to dissolve faster than organisms can rebuild them. Reef ecosystems collapse completely, leaving no refuge for dependent species. Food webs disintegrate. Primary producers falter. Herbivores starve. Predators vanish. This is not a selective pruning, it is a systemic failure. The foundational chemistry of the biosphere has turned against life. By the height of the extinction, the numbers are almost incomprehensible. Up to 96% of marine species disappear. Trilobites, which survived previous extinctions, vanish forever. Corals are reduced to a handful of lineages: brachiopods, echinoderms, mollusks. Entire branches of the marine tree of life are severed. On land, the devastation is scarcely less severe. 70% of terrestrial vertebrate species die out. Forests collapse. Insect populations crash. Soils erode without plant cover, washing nutrients into rivers that carry them uselessly into dead seas. The land becomes barren, stripped of resilience. Why does recovery fail this time? In previous extinctions, refugees existed: cooler regions, deeper waters, isolated ecosystems that could serve as reservoirs of diversity. During the end Permian, there are almost none. Heat is global, anoxia is widespread, acidification is pervasive, poison rises from the depths. Even if organisms survive one stressor, another awaits. There is no stable baseline to adapt to. Evolution stalls because selection has nothing to select from. Reproduction slows or stops. Generation times lengthen under stress. Mutation rates increase, but beneficial adaptations cannot spread through collapsing populations. The evolutionary engine sputters. The biosphere does not merely shrink, it nearly shuts down. And yet, life does not end completely. The survivors are not heroes. They are minimalists. Small-bodied organisms persist because they require fewer resources and tolerate environmental swings more easily. Generalists survive because they do not rely on a single food source. Burrowing animals endure by retreating underground, where temperatures and chemistry fluctuate less violently. Microbes thrive, as they always have, exploiting niches toxic to others. In the oceans, certain bacteria flourish in anoxic conditions, reshaping global chemistry even further. On land, a handful of hardy vertebrates cling to existence, ancestors of future reptiles and mammals, reduced in size, slowed in metabolism, stripped of ecological dominance. These survivors are not advancing, they are enduring. For millions of years after the extinction peak, Earth remains locked in a state of biological depression. Reef systems do not recover, forests are sparse, ecosystems are simple, unstable, fragile. The fossil record records a long silence where diversity should be. This is the aftermath of the greatest dying. A planet that almost fails. Only after 5 to 10 million years do signs of recovery begin to appear. And even then, the world that emerges is unfamiliar. The old orders are gone. The rules have changed. Evolution resumes, but from a radically simplified starting point. The end Permian extinction stands alone in Earth's history, not just for its scale, but for its completeness. It demonstrates something terrifyingly clear. When climate, chemistry, and geology align against life, survival becomes a statistical anomaly. Earth came closer to sterility than at any other time since life began. For a long while, it nearly stays that way. For millions of years, the Earth almost stays dead. The world after the end Permian was a shadow of its former self. The seas, once teeming with unimaginable diversity, were silent. Reefs that had towered over shallow continental shelves were gone, leaving only barren substrates. The ocean's chemical balance remained hostile for millions of years, a mosaic of oxygen-depleted basins interspersed with tiny habitable patches. Life that had survived the catastrophe now faced a planet that seemed almost designed to frustrate recovery. In these fragile refuges, survival was not luxury, it was endurance. Species that had escaped extinction were reduced in number, their populations fragmented across scattered, isolated environments. Genetic diversity was low, and small population sizes made them vulnerable to further environmental shifts. Reproduction was slower, growth stunted, and ecological interactions precarious. Evolution, normally a prolific force, was constrained by these bottlenecks, forcing a long, tentative rebuilding of ecosystems. The first signs of recovery appeared in the oceans. Certain hardy lineages, bivalves, ammonoids, and some small fish began to diversify, but at a slow pace. Reef-building organisms returned, but they were simpler than those of the Permian. Coral stromatoporoid reefs were sparse and fragile, forming only in limited areas where water conditions allowed. Oxygen levels fluctuated dramatically, and seasonal anoxia could wipe out entire communities before they had a chance to stabilize. The pace of life was dictated by the planet's chemistry, not biology. On land, the story was no less precarious. Forests were sparse, mostly composed of ferns and lycopsides, limited to wetlands and river valleys. Insects survived in reduced numbers, but many giant forms of the Carboniferous had vanished. The terrestrial vertebrates that endured were mostly small, generalized species capable of surviving harsh conditions. Amphibians persisted near water, while the earliest reptiles began to diversify slowly. The amniotic egg, once a minor innovation, became a critical tool for survival on dry land, allowing lineages to escape the vulnerabilities of aquatic reproduction. The bottleneck created by the end Permian extinction reshaped evolution. Traits that had been advantageous in a rich, complex ecosystem became liabilities. Dominant predators and large-bodied organisms largely vanished. Survival favored small size, generalist diets, tolerance of fluctuating oxygen, and the ability to exploit marginal habitats. These traits would influence the trajectory of life for tens of millions of years, creating lineages predisposed to resilience rather than dominance. In the recovering seas, fish began to diversify anew. Ray-finned fish, previously minor components of marine ecosystems, now found niches to exploit. Sharks and other cartilaginous fish survived the extinction in reduced numbers, but began to expand as prey availability gradually increased. The first major adaptive radiations in marine vertebrates occurred against this backdrop of scarcity and instability, laying the foundation for modern fish lineages. Terrestrial life too slowly found its footing. Reptiles, though initially limited in diversity, began experimenting with form and function. Certain lineages, archosaurs among them, developed features that would later support the dominance of dinosaurs. Limbs became stronger, postures more erect, and metabolic strategies more efficient. The survivors of the Permian extinction were shaping the blueprint for future ecosystems, even as they themselves navigated a world still inhospitable and unpredictable. The environment remained volatile. Climate oscillations persisted, with alternating arid and humid periods. Sea levels fluctuated, and oxygen-depleted waters still threatened marine recovery. Carbon dioxide levels were elevated, warming the planet and destabilizing weather systems. Despite this, life's persistent pressure slowly restructured ecosystems. Simple food webs became more complex. Predators emerged again, initially small, opportunistic species capable of exploiting niches left vacant by the extinction. Prey populations diversified in response, and trophic interactions gradually stabilized. Evolutionary innovation was constrained by scarcity, but it was far from halted. New adaptations appeared in surviving lineages, driven less by competition than by the need to endure fluctuating conditions. Morphological diversity increased as species experimented with feeding strategies, body plans, and reproductive modes. Yet recovery was uneven. Some regions remained near sterile, while localized pockets of life flourished, forming centers of diversification that would seed the rest of the planet over millions of years. The archosaurs exemplify this emerging potential. Small, upright reptiles, initially minor players in Permian ecosystems, begin exploiting niches that had been inaccessible in richer, more competitive times. Their skeletal structures allow efficient locomotion on land, and their metabolic flexibility gives them an advantage in extreme conditions. Over the coming tens of millions of years, these lineages will evolve into the dominant terrestrial vertebrates of the Mesozoic, shaping entire ecosystems and redefining the relationship between predator and prey. In both sea and land, life is beginning to experiment again, though cautiously. The fossil record shows incremental increases in species richness, complexity, and ecological interaction. But the world remains fragile. Recovery is not a return to the past. It is a reconstruction under entirely new rules. Extinction has rewritten the blueprint of life. The survivors are the architects of a new era, but they are building on a foundation still unstable, still unforgiving. The recovery of life after the Permian extinction is measured in millions of years. It is a testament to persistence rather than triumph. For every lineage that flourishes, countless others vanish in the delicate balance between opportunity and danger. Evolutionary bottlenecks prune the tree of life, leaving certain paths permanently closed, while opening new avenues for innovation. The survivors, small, adaptable, and resilient, define the template for the ecosystems of the Mesozoic, the era that will follow. By the late early Triassic, ecosystems have regained structure, though simplicity still dominates. Shallow seas harbor fish, bivalves, and early reptiles, while forests gradually recolonize floodplains. Complex trophic interactions begin to emerge, but the scale and diversity of life remain below pre-extinction levels. The Earth is breathing again, though it is a cautious, measured pulse. Life has endured, but it has changed. The massive dominant organisms of the Permian are gone, replaced by smaller, more generalized forms capable of withstanding extremes. The survivors carry the scars of catastrophe in their DNA, their physiology, and their ecological strategies. They are prepared to endure, but not yet to dominate. The seeds of future reigns are present in these survivors. Archosaurs, small reptiles emerging from refuges, will one day ascend to dominate terrestrial ecosystems. Fish lineages begin to fill the oceans, setting the stage for modern vertebrate evolution. Plants continue to spread across continents, stabilizing soils and modifying climate in ways that will shape terrestrial ecosystems for millions of years. The world that emerges from the Permian extinction is not the same Earth that entered it. Life is scarred, ecosystems simplified, and evolutionary potential constrained, but the survivors are resilient, adaptable, and poised to define the next chapter in the planet's story. The next rulers of Earth are waiting. The Triassic world is a landscape of experimentation. After the long, uncertain recovery from the end Permian extinction, life has begun to diversify again, but it exists in a fragile balance. The seas are repopulated by fish, ammonoids, and small marine reptiles, while on land, forests, though less dense than in the Carboniferous, cover river valleys and floodplains. Swamps and wetlands provide refuge for amphibians, while reptiles explore the arid interiors of Pangaea, their small, flexible forms allowing them to survive the extremes of heat and drought. Among the terrestrial vertebrates, several groups are quietly rising. Early archosaurs, relatives of crocodiles and dinosaurs, expand across continents, experimenting with posture, metabolism, and predation strategies. They are small at first, opportunistic, but their skeletal structures hint at the dominance they will eventually achieve. Mammal ancestors, the cynodonts, scuttle through undergrowth, nocturnal and cautious, adapting to niches that favor stealth, intelligence, and endurance. Together, these lineages are sowing the seeds of the Mesozoic, though they do not yet command the planet. The Triassic climate is volatile. The supercontinent Pangaea stretches from pole to pole, creating extreme continental interiors. Deserts bake under the sun, while coastal regions experience seasonal monsoons and intense storms. Temperature swings are extreme, often shifting dozens of degrees between day and night or seasonally. Ocean currents, constrained by the vast continental arrangement, are sluggish, creating regions of stagnant water and periodic low oxygen zones. Life is forced to adapt to unpredictability. Specialization is dangerous. Flexibility is survival. In the oceans, the first true marine reptiles emerge. Ichthyosaurs begin to take shape, their streamlined bodies adapted for pursuit. Placodonts and nothosaurs appear in shallow seas, experimenting with forms and diets that will later dominate marine ecosystems. Coral reefs, though less abundant than before the Permian, re-establish in patches, providing structure for a renewed, though fragile, biodiversity. On land, plant life stabilizes some environments, but also introduces new pressures. Gymnosperms, conifers and seed ferns begin to dominate arid regions, creating forests capable of withstanding heat and drought. Vegetation modifies soils, influences erosion, and contributes to localized climate patterns, shaping rainfall and temperature variability. In some regions, forest fires become a regular occurrence, fueled by high oxygen levels and dry conditions. Life must navigate both abundance and threat simultaneously. Volcanism plays a growing role in shaping the environment. Rift zones along the edges of Pangaea release lava and gases as the supercontinent begins to fracture. While these events are not yet catastrophic on a global scale, they contribute to long-term climatic instability. Carbon dioxide emissions from repeated eruptions reinforce warming, while ash clouds intermittently block sunlight, creating short-term cooling episodes. Acid rain affects freshwater systems, challenging amphibians and early reptiles. Nutrient pulses in rivers and oceans drive localized productivity, sometimes triggering eutrophication and low oxygen conditions in coastal seas. The combination of climatic extremes, volatile oceans, and emerging volcanism creates a world of opportunity and danger. Life is experimenting, evolving, and expanding, yet it is never far from the edge. Species that cannot tolerate temperature swings, water scarcity, or oxygen fluctuations are eliminated before they can establish dominance. In this environment, evolutionary success favors adaptability, mobility, and resilience rather than size or specialization. Dinosaurs, though still small and marginal in ecological terms, begin to appear. Their presence is subtle, hidden among more dominant reptiles, yet their evolutionary strategy, upright posture, efficient locomotion, and the potential for rapid growth, positions them to capitalize on future ecological vacuums. Mammal ancestors, small and nocturnal, rely on intelligence, speed, and flexibility to survive. Crocodile relatives maintain semi-aquatic niches, benefiting from a balance of terrestrial and aquatic habitats that buffer them against extremes. The world of the Triassic is dynamic, a planet of both experimentation and constraint. The ecological canvas is being repainted after the Permian collapse, yet the broad outlines are fragile. Ecosystems are complex, but they remain untested by global catastrophe on the scale of the Permian extinction. Every eruption, every heatwave, every drought carries the potential to tip the balance. Beneath the surface, the planet itself is restless. Tectonic forces are pushing Pangaea toward fragmentation. Rift zones widen, releasing magma and gases. Earthquakes crack the crust. Seafloor spreading accelerates along nascent oceans, altering currents and regional climates. The physical stresses of continental rearrangement ripple through ecosystems in subtle, sometimes invisible ways. Life, in turn, responds. Species migrate, adapt, and diversify in response to shifting habitats. Predators follow prey. Plants colonize newly exposed soils. Insects evolve alongside flowering plants, exploiting new niches. Ecological networks become intricate but remain brittle. One extreme event, a volcanic eruption, a flood, a prolonged drought, could unravel them in a matter of years, a geologic heartbeat in the life of the supercontinent. The Triassic world is a delicate experiment. It is a stage set for future dominance by new groups, but it has not yet faced the ultimate test. Environmental stress accumulates gradually. Volcanic tension beneath the continents, chemical changes in the oceans, temperature extremes on land. Life is resilient, but resilience is not infinite. The stage is prepared quietly for another catastrophic reset, one that will challenge the planet's fragile balance and once again reshape the course of evolution. The planet fractures, and so does life. The Triassic world had been a fragile tapestry of recovery, stitched together from the ruins of the Permian and shaped by millions of years of experimentation. Life was diverse but uneven, and the planet itself remained restless. Then, around 201 million years ago, the Earth entered its next great reset, the end Triassic extinction, a cataclysm that would eliminate competitors and create the conditions for dinosaurs to rise. The trigger lay in the very crust beneath the supercontinent Pangaea. In what would become one of the largest volcanic events in Earth's history, the Central Atlantic Magmatic Province, or CAMP, began to erupt. Unlike the slow trickle of typical volcanism, CAMP was massive and sustained. Basaltic lava poured across vast regions of what is now eastern North America, northern Africa, South America, and Western Europe. The eruptions were not uniform. They came in pulses, each lasting thousands of years, each accompanied by the release of enormous quantities of gases into the atmosphere. Carbon dioxide levels skyrocketed. Methane, released from subsurface reservoirs disturbed by magma intrusions, amplified greenhouse effects. Sulfur dioxide, released as lava interacted with sedimentary deposits, created acid rain that pockmarked landscapes and poisoned freshwater systems. These gases, injected into the atmosphere at unprecedented rates, rapidly shifted the climate. Global temperatures soared. Some estimates suggest an average rise of 5 to 10 degrees Celsius, perhaps more in continental interiors where heat could accumulate. The oceans reacted violently. Warmer waters held less dissolved oxygen, and stratification intensified, creating widespread low oxygen zones. Simultaneously, carbon dioxide dissolved into seawater, forming carbonic acid and lowering pH levels. Calcifying organisms, mollusks, corals, and certain plankton, struggled to build shells in increasingly corrosive conditions. Reef systems that had recovered since the Permian began to fail again, collapsing under the dual pressures of acidification and anoxia. This environmental upheaval did not strike evenly. Many of the dominant terrestrial reptiles of the Triassic, phytosaurs, etosaurs, large crocodile-like forms, and several groups of heavily armored archosaurs, succumbed. They had flourished in stable niches across the supercontinent, but when conditions changed rapidly, their specializations became liabilities. Large body size, high metabolic demand, and narrow ecological tolerance worked against them. Many species that had survived the Permian only to rise in the Triassic vanished completely. The extinction occurred in pulses. Evidence from sedimentary records suggests multiple episodes over hundreds of thousands of years, each corresponding to surges in volcanic activity. Each pulse delivered stress to the biosphere. One wave of eruptions triggered warming, another acidified the oceans, yet another poisoned freshwater habitats. Life struggled to stabilize between these events, but each recovery was short-lived. Ecosystems never regained equilibrium. Yet even amid this catastrophe, survival was not random. Certain lineages endured, not because they were the strongest, but because they were adaptable. Dinosaurs, still small and marginal in the Triassic, survived by exploiting niches others could not. Their upright posture, efficient locomotion, and relatively high reproductive rates allowed them to navigate shifting habitats and escape predation. Early mammals, tiny and nocturnal, persisted in marginal environments, feeding on insects and seeds that remained available despite ecological collapse. Crocodilian relatives, semi-aquatic, flexible, and capable of enduring both droughts and floods, also endured, occupying stable riverine and coastal habitats. The oceans tell a similar story. Survivors were mostly small, opportunistic species capable of tolerating fluctuating oxygen levels and acidic waters. Mollusks with rapid reproductive cycles, certain bivalves, and resilient ammonoids persisted. Marine reptiles, though affected, found refuge in coastal zones less influenced by acidification or in deeper waters buffered from sudden temperature swings. Microbial life thrived in toxic, low-oxygen basins, forming a foundation for eventual recovery. The end Triassic extinction also reshaped evolutionary trajectories in subtle but permanent ways. The collapse of large dominant reptiles opened ecological space for dinosaurs. Where once their Triassic competitors had held sway, now opportunities existed for archosaurs to expand in both size and diversity. Mammal ancestors, though small and inconspicuous, could exploit nocturnal niches and avoid direct competition with larger predators. Crocodilians maintained their semi-aquatic strongholds, waiting for opportunities to diversify when conditions stabilized. Environmental pressures continued to favor adaptability over specialization. Generalist feeders, species capable of tolerating extreme temperature ranges, and organisms that could exploit marginal habitats were disproportionately represented in post-extinction communities. Traits that once had been secondary, small size, flexibility, rapid reproduction, became decisive advantages. Life was no longer thriving in a stable world. It was navigating a planet in near constant flux. The chemical upheavals in the oceans also had lasting impacts. Low oxygen and acidification filtered species based on physiological tolerance, favoring lineages that could survive extreme environmental stress. Calcifying species, once prolific, were dramatically reduced, paving the way for new forms to emerge in the Jurassic. Nutrient cycles, previously dominated by stable ecosystems, now relied on opportunistic and resilient microbes, creating a foundation for new food webs. On land, forests were also reshaped. Gymnosperms, conifers and seed ferns remained dominant, but repeated episodes of volcanic ash, acid rain, and drought repeatedly thinned their distribution. Swamps contracted. Fires, fueled by increased oxygen levels and dry conditions, became more frequent. Early reptiles and mammal ancestors had to navigate a world where both food sources and shelter were inconsistent, selecting for mobility, opportunism, and resourcefulness. Volcanism, climate instability, and chemical disruption acted together to rewrite the map of survival. This extinction was not merely a filter, it was a reset, clearing ecological space in both oceans and on land. Ecosystems that had stabilized since the Permian were uprooted, and new opportunities emerged for lineages previously confined to the margins. The fossil record shows a rapid turnover in dominant species. Triassic reptiles, once the rulers of terrestrial ecosystems, vanish. Large amphibians decline. Certain marine invertebrates disappear entirely, while smaller, more flexible species persist. Dinosaurs, initially minor and inconspicuous, are positioned to expand into vacant ecological niches. Mammals, still small, find safety in nocturnal and hidden habits. Crocodilians occupy the remaining stable aquatic zones. In both sea and land, resilience and adaptability define survival. By the end of the extinction, approximately 50% of all species, land and sea, are gone. In some marine groups, the loss is even higher. Competition has been dramatically reduced. The playing field for the next chapter of life is remarkably open. Species that endure the end Triassic extinction do not dominate because they were powerful or numerous. They dominate because they could withstand instability, move between habitats, and exploit unpredictability. The consequences of this reset echo through deep time. Dinosaurs, once marginal, begin to expand in both size and diversity. Archosaurs evolve more varied forms, experimenting with posture, locomotion, and predatory strategies. Mammal ancestors, though small, exploit nocturnal niches, laying the groundwork for intelligence and endothermy in the distant future. Crocodilians maintain semi-aquatic strongholds, ensuring their survival for the next 200 million years. The oceans slowly recover, with reefs and marine ecosystems re-establishing themselves over millions of years. Opportunistic lineages fill vacant niches. Food webs grow more complex, but the survivors carry the mark of extinction. Generalist forms dominate, while specialized lineages remain rare until stability returns. Environmental pressures continue to select for flexibility, mobility, and tolerance, creating a world where adaptability is more important than brute strength. The end Triassic extinction demonstrates a pattern repeated throughout Earth's history. Mass extinctions do not necessarily reward the strongest. They reward the survivors capable of enduring extremes. Catastrophe reshapes not only which species exist, but also how life evolves. It prunes the tree of life, but it also opens pathways for innovation and dominance by lineages that previously occupied the margins. In the aftermath, dinosaurs occupy the niches once held by Triassic competitors. Their expansion is not sudden, it is gradual, measured by ecological opportunity. But the trajectory is clear. Archosaurs, now largely unchallenged on land, begin to diversify rapidly. Mammal ancestors continue their quiet evolution, and crocodilian lineages solidify their presence in semi-aquatic habitats. Life, shaped by survival under stress, is poised for the Mesozoic era, a period that will see the rise of some of the largest and most iconic organisms in Earth's history. One lineage now inherits the Earth. Life on Earth after the upheavals of the Triassic enters a period of remarkable stability and expansion. The Mesozoic, encompassing the Jurassic and Cretaceous periods, is defined by the rise of dinosaurs as the dominant terrestrial vertebrates, the refinement of ecosystems across continents, and the slow, steady transformation of both land and sea into environments rich with diversity and complexity. For the first time in tens of millions of years, Earth seems balanced. The continents, though still in motion, are gradually drifting apart from the supercontinent Pangaea. Shallow seas spread between them, creating coastlines and inland seas that act as buffers against extreme continental temperatures. Ocean currents begin to stabilize, distributing heat and nutrients more evenly than in the chaotic Triassic. Climates become more predictable, though extremes still exist in polar regions. In tropical and temperate zones, rainfall and seasonal cycles support lush forests and grass-like fernlands, while deserts remain confined to some continental interiors. Dinosaurs flourish in this environment. They are no longer marginal experimental creatures but established rulers of land ecosystems. Herbivorous lineages, sauropods, stegosaurs, ornithopods, dominate the floodplains and forests, growing to extraordinary sizes. Massive sauropods stretch their necks into the canopies, consuming vegetation at scales unimaginable in previous eras. Their sheer mass reshapes the land itself, compressing soils and redistributing nutrients through their waste. Predatory dinosaurs, from the agile allosaurs to early tyrannosaur relatives, patrol these landscapes, their hunting strategies refined by millions of years of evolutionary competition. Ecological complexity deepens. Forests are layered and stratified. Canopy dwellers exploit elevated niches. Ground-level herbivores feed on low vegetation, and small dinosaurs and mammals occupy the shadows beneath the trees. Birds have yet to appear in significant numbers, but the precursors to modern avian lineages experiment with feathers, gliding, and thermal regulation. Insects diversify alongside plants, pollinating and herbivorizing, creating intricate food webs that sustain both small and large vertebrates. Flowering plants, or angiosperms, make their first appearance during the mid to late Cretaceous. Their introduction subtly transforms ecosystems. Flowers and fruits offer new food sources, attracting insects, small reptiles, and the early mammals that exploit these resources. Angiosperms begin to displace older gymnosperms in some environments, creating more diverse forests with new patterns of growth, competition, and reproduction. Seeds and fruit allow plants to colonize disturbed soils and expand more rapidly than before, further stabilizing terrestrial ecosystems. Marine life also flourishes. Oceans teem with ammonites, marine reptiles, early teleost fish, and diverse invertebrate communities. Reef ecosystems re-establish themselves fully, with corals, sponges, and other calcifying organisms constructing complex habitats. Planktonic species dominate nutrient cycling, forming the foundation of productive food chains that support larger predators, including ichthyosaurs, plesiosaurs, and mosasaurs in the Cretaceous. Sharks and rays expand their ecological niches, hunting in open waters and along coastal shelves. For millions of years, the Earth appears deceptively stable. Ecosystems are resilient. Evolutionary experimentation continues, but it occurs within predictable frameworks. Dinosaurs diversify into nearly every terrestrial niche: giants and small forms, fast runners and armored tanks, soaring pterosaurs in the skies, semi-aquatic predators along the shores. Mammals remain small but adaptive, nocturnal foragers exploiting niches that reduce competition with dominant dinosaurs. Crocodilians maintain their semi-aquatic strongholds, largely unchanged in form but refined in behavior and hunting strategy. Yet beneath this apparent calm, subtle stresses accumulate. Volcanic activity continues at a low level, releasing carbon dioxide and contributing to long-term climate fluctuations. Sea levels rise and fall over millions of years, expanding and contracting shallow seas that connect or isolate ecosystems. Continental drift reshapes geography, altering river courses, isolating populations and driving speciation. While the world seems balanced, these slow forces quietly set the stage for future disruption. Ecological interactions are more complex than ever. Herbivorous dinosaurs influence plant evolution through selective feeding and trampling, shaping forest structure. Predators drive behavioral adaptations among prey, including social behavior, camouflage, and herd formation. In the oceans, predator-prey dynamics between marine reptiles and fish shape schooling behavior and migration patterns. Ecosystems are networks of feedback, energy flows, and interdependence that have matured since the turbulent Mesozoic beginnings. Despite these advances, life remains vulnerable to sudden external shocks. The stability of ecosystems, while impressive, depends on long-term climatic and geological trends. Species have adapted to gradual shifts over millions of years, but sudden extreme events, volcanic outbursts, asteroid impacts, or abrupt climate changes remain outside the range of evolutionary preparedness. This latent vulnerability is invisible in the fossil record, concealed by millions of years of apparent balance and flourishing. In this long calm, dinosaurs dominate, but their reign is not unchallenged. Early birds, mammals, and various reptiles exist in the shadows, experimenting with flight, burrowing, nocturnality, and other survival strategies. These minor players are preparing in evolutionary silence, quietly refining traits that may prove critical when catastrophic events reshape the planet. Plants too, from ferns to angiosperms, continue to evolve, increasing the complexity and redundancy of ecosystems. Biodiversity reaches levels that would have seemed impossible in the Permian and Triassic, yet the foundation remains sensitive to disruption. The oceans, while productive, are also finely balanced. Oxygen gradients, temperature stratification, and nutrient distribution create subtle pressures that maintain species diversity. Coral reefs flourish in pockets where conditions are ideal, but remain sensitive to acidification or temperature spikes. Marine reptiles, abundant and diverse, patrol the seas with dominance, yet their survival depends on the continued productivity of plankton, fish, and shellfish. Any major disruption to this delicate equilibrium could cascade across entire food webs. Across continents, life seems invincible, yet the calm is deceptive. The world is poised, intricate and mature, a complex system honed over millions of years of recovery, extinction and experimentation. Dinosaurs rule as apex herbivores and predators. Mammals operate quietly under their shadow, and ecosystems have expanded to fill every available niche. Plant and animal life co-evolve in intricate networks of dependence and competition, creating the appearance of a stable, eternal order. But stability on Earth is never permanent. External forces, asteroidal collisions, volcanic cataclysms, climate shifts, remain capable of disrupting the most finely tuned of ecosystems. The fossil record shows that mass extinctions are inevitable, even in seemingly balanced worlds. For tens of millions of years, life has endured shocks and recovered, each time emerging in new forms, restructured and redirected. The calm of the Jurassic and Cretaceous is no exception. It is the quiet before the storm, the final flourishing before a sudden catastrophic reset. Across oceans and continents, the stage is set. Dinosaurs dominate the land. Marine reptiles rule the seas. Mammals and birds linger in the shadows, quietly evolving. Forests and flowering plants shape environments that appear stable, resilient, and productive. The planet has recovered from previous cataclysms and matured into a complex, interconnected biosphere. Yet this calm, carefully constructed over millions of years, is fragile. One event, sudden and external, can undo the intricate balance, wipe out dominant species, and reset the evolutionary trajectory of life. The next extinction does not arise from land or sea. It comes from the sky. The end of the Cretaceous was not quiet. The planet, flourishing under the reign of dinosaurs, appeared balanced, even eternal. Forests sprawled across continents, seas brimmed with life, and the intricate web of ecosystems functioned with a precision honed over tens of millions of years. Yet the Earth, for all its stability, had always been vulnerable to forces beyond the comprehension of its inhabitants. Around 66 million years ago, the next mass extinction arrived in a flash, a cosmic event that would reset life in ways both immediate and enduring. The trigger was the asteroid known today as the Chicxulub impactor, striking what is now the Yucatan Peninsula in Mexico. Roughly 10 to 15 kilometers in diameter, this celestial body carried energy equivalent to billions of nuclear bombs detonating simultaneously. The impact released a force so immense that it vaporized rock, sent molten debris into the atmosphere, and generated shock waves that radiated around the globe. The crater itself spans nearly 200 kilometers, a scar etched into the planet's crust, and the ejector it produced blanketed Earth, raining molten spherules and dust across oceans and continents. The immediate effects were catastrophic. In the region of impact, everything within thousands of kilometers was annihilated in moments. Forests flattened, creatures incinerated or crushed by the immense shock waves, rivers vaporized and landscapes scoured. Firestorms ignited across vast areas as ejecta re-entered the atmosphere, heating the surface to temperatures lethal to unprotected organisms. In the hours and days that followed, darkness descended over the planet. Dust and aerosols blocked sunlight, plunging Earth into a dramatic cooling period known as an impact winter. Photosynthesis ceased almost immediately. Plants across continents were deprived of light, halting growth and reproduction. Herbivorous dinosaurs starved, unable to find sufficient foliage to sustain their enormous metabolisms. Predators, in turn, faced the collapse of the prey base, initiating a cascading extinction through terrestrial food webs. In the oceans, plankton populations fell dramatically under the combined stresses of darkness, temperature shifts, and chemical perturbations. Reef ecosystems, already sensitive to minor disruptions, began to fail, triggering secondary extinctions among fish, mollusks, and marine reptiles. But the asteroid alone was not the sole agent of disaster. For millions of years leading up to the impact, the Deccan traps in India had been releasing vast quantities of volcanic gases. Lava flows blanketed hundreds of thousands of square kilometers, and the continuous emission of carbon dioxide and sulfur dioxide contributed to long-term climate warming and ocean acidification. While this volcanic activity had not precipitated immediate global catastrophe, it had already stressed ecosystems, lowered thresholds of resilience, and made life more vulnerable to sudden shock. The asteroid, therefore, struck a planet already on edge, amplifying the effects of global catastrophe. The combination of darkness, fire, cooling, and acid rain created a perfect storm for extinction. Surface temperatures initially plummeted, creating an abrupt thermal shock that further challenged survival. In the oceans, a sudden loss of primary producers destabilized food chains. Oxygen levels in shallow seas dropped in response to temperature changes and nutrient imbalances. Acidification hindered the ability of calcifying organisms to maintain shells and skeletons. Coral reefs, already under stress, largely disappeared. Larger marine reptiles, including mosasaurs and plesiosaurs, could not survive the sudden collapse of food availability. On land, the dinosaurs faced multiple pressures simultaneously. Large body size, once an advantage in dominating ecosystems, became a liability. Sauropods, had they survived the initial impact, were quickly starved. Their massive energy requirements could not be sustained in a world of collapsing forests and dying herbivores. Theropods, including tyrannosaurs and raptors, faced a similar crisis. Even smaller dinosaurs, capable of faster reproduction, were subject to habitat loss, fires, and disrupted ecological networks. Their evolutionary strategy, honed over millions of years, was adapted to gradual change, not sudden catastrophic shock. Survival depended on traits that could buffer species against unpredictability. Small size conferred multiple advantages: reduced food requirements, faster reproductive cycles, and the ability to exploit marginal or subterranean habitats. Animals capable of burrowing or seeking shelter beneath the soil or in crevices were insulated against the heat of firestorms and the cold of the impact winter. Omnivorous diets or the ability to scavenge allowed flexibility when specific food sources vanished. Birds directly descended from theropod dinosaurs, but already small, mobile, and adaptable, survived by foraging in niches inaccessible to larger species. Mammals, though diminutive and primarily nocturnal, exploited insect populations, seeds, and detritus, insulating themselves from the collapse of large-scale ecosystems. Amphibians, often inhabiting freshwater refuges and capable of enduring environmental extremes, persisted where larger vertebrates could not. Plant life, too, endured selectively. Seeds, spores, and pollen provided mechanisms to survive prolonged darkness, fires, and chemical stress. Gymnosperms and angiosperms with hardy reproductive strategies propagated even as forests were decimated. These resilient lineages would seed the regrowth of ecosystems in the Paleogene, forming the foundation for new food webs. The extinction also highlights the vulnerability of specialized niches. Dinosaurs, despite their dominance for over 160 million years, were constrained by size, dietary specialization, and dependence on established food chains. The largest herbivores required abundant foliage. The apex predators relied on prey capable of sustaining their massive energy needs. When ecosystems failed simultaneously, there were no refuges large enough or stable enough to buffer these dependencies. In contrast, small, generalized organisms could navigate fragmented habitats, exploit a wider array of resources, and endure periods of scarcity. In marine systems, the effects were equally profound. Ammonites, cephalopods with intricate shells, largely disappeared. Marine reptiles, dependent on a continuous food supply of fish and smaller prey, were decimated. Planktonic organisms experienced near-total mortality in some regions, causing cascading effects through food webs. Survivors were primarily small, opportunistic species capable of enduring low light, variable oxygen levels, and acidified waters. Microbial communities thrived where complex organisms failed, stabilizing chemical cycles and providing the first hints of recovery. The fossil record also suggests that environmental stress persisted long after the initial impact. Acid rain and ash-laden soil altered terrestrial habitats, slowing plant regrowth. Ocean chemistry, destabilized by acidification and nutrient imbalance, required millennia to normalize. Recovery was not instantaneous. It was measured in hundreds of thousands to millions of years. During this period, ecological opportunity favored the survivors, birds, mammals, amphibians, and certain plants, to expand and diversify in the absence of large, dominant reptiles. One of the most significant outcomes of the end Cretaceous extinction is the redistribution of ecological opportunity. Dinosaurs, once the unrivaled rulers of terrestrial ecosystems, were replaced by lineages capable of enduring extreme environmental fluctuations. Mammals, small and adaptable, exploited nocturnal, arboreal, and burrowing niches. Birds radiated into diverse forms, occupying aerial and forested spaces. Reptiles, such as crocodilians, retained semi-aquatic habitats, while surviving amphibians and fish recolonized freshwater systems. Seeds and hardy plant lineages re-established terrestrial primary production, supporting the rebuilding of complex ecosystems. The extinction demonstrates the interplay of speed, scale, and pre-existing stress. The asteroid struck suddenly, but its effects were magnified by volcanism, climate instability, and ecological pressure already present on Earth. Species that had survived previous mass extinctions were not immune. Survival depended less on dominance or size and more on flexibility, dormancy, and ecological generalism. Life's resilience was tested not by gradual change but by instantaneous global catastrophe. In the aftermath, the world is transformed. Dinosaurs, the dominant vertebrates for over 100 million years, vanish from nearly every terrestrial ecosystem. Ecosystems are reduced in complexity. Forests, grasslands, and coastal environments are depopulated. Oceans are depauperate. Yet this devastation, paradoxically, creates the conditions for evolutionary experimentation and expansion. The survivors, small, adaptable, and opportunistic, inherit a planet almost entirely cleared of competition. Evolution begins anew under radically different constraints and opportunities. For the first time in tens of millions of years, mammals have ecological space to expand. Birds radiate into aerial niches previously dominated by non-avian dinosaurs. Amphibians recolonize freshwater systems, and resilient plant lineages establish the base for renewed forests. Marine ecosystems gradually rebuild around surviving invertebrates and fish. The planet once again begins a slow recovery, but the evolutionary landscape is forever altered. The end Cretaceous extinction is a stark reminder that dominance is ephemeral. For all their size, power, and evolutionary refinement, dinosaurs were unprepared for sudden external catastrophe. Survival favored adaptability, small size, and flexible ecological strategies. From this crucible, new lineages emerged to inherit the Earth, setting the stage for mammals, birds, and eventually intelligence itself. From the ashes, intelligence begins to rise. After the extinction of the non-avian dinosaurs, the planet was a canvas emptied of its most dominant terrestrial vertebrates. For over 160 million years, dinosaurs had monopolized forests, plains, and skies, leaving mammals and small reptiles confined to marginal niches, nocturnal habits, dense underbrush, or burrows underground. With the colossal predators and mega-herbivores gone, the ecological playing field opened in ways that allowed mammals to flourish, diversify, and experiment with forms and behaviors that had previously been suppressed. The Paleogene world, beginning around 66 million years ago, was a time of rapid evolutionary expansion. Forests regrew, wetlands stabilized, and grasslands gradually spread, creating a variety of habitats previously inaccessible. Mammals, small and generalized survivors, now encountered unprecedented opportunities. Rodent-like species radiated quickly, exploiting seeds, insects, and detritus. Carnivorous mammals evolved to fill predatory niches once dominated by theropods, while herbivorous mammals diversified into browsing and grazing forms. Within a few million years, mammals went from inconspicuous nocturnal creatures to a wide array of ecological specialists, from semi-aquatic swimmers to tree-dwelling climbers. This adaptive radiation was not merely a consequence of open niches. The early Cenozoic climate played a critical role in shaping mammalian evolution. The Earth warmed in the Paleocene and Eocene, creating lush tropical forests that supported arboreal species. Later cooling events and the formation of polar ice caps introduced cycles of climate oscillation, driving innovation in thermoregulation, metabolism, and behavioral flexibility. Species that could survive both heat and cold, wet and dry periods were selected for, fostering intelligence, complex social behavior, and problem-solving skills. Among the lineages that would shape the future were the early primates. Tiny, nocturnal, and arboreal, they navigated forests with skill, relying on keen vision, dexterous hands, and acute perception. The selective pressures of climbing, leaping, and locating food in complex three-dimensional environments contributed to the evolution of larger brains relative to body size. This was an early experiment in cognition, a subtle reshaping of neural architecture driven by ecological demands rather than foresight. Simultaneously, other mammalian groups adapted to terrestrial, aquatic, and semi-aquatic niches. Ungulates began to explore grasslands, developing teeth capable of grinding tougher vegetation. Predators evolved sharper teeth, more efficient locomotion, and refined hunting strategies. Social structures emerged as cooperative hunting and complex foraging behaviors conferred survival advantages. Each ecological experiment, arboreal, burrowing, grazing, hunting, was a step in a broader pattern of mammalian diversification that would eventually encompass nearly every habitat on the planet. The fossil record shows repeated pulses of speciation, often tied to climate change. Cooling periods forced migrations, fragmentation of populations, and isolation, accelerating evolutionary divergence. Ice ages sculpted the physiology and behavior of mammals, selecting for endurance, adaptability, and intelligence. Environments that fluctuated unpredictably favored species capable of flexible feeding strategies, rapid reproduction, and novel problem-solving. These pressures gradually set the stage for more sophisticated cognition, planning, and social organization. The oceans and freshwater systems also contributed to mammalian experimentation. Semi-aquatic lineages, such as early cetaceans, began to adapt to aquatic life, transforming limbs into flippers, developing echolocation and exploiting marine food webs. This diversification illustrates a key principle of post-extinction evolution. Life does not simply replace what was lost, it innovates, finding entirely new ways to interact with the environment. Throughout the Cenozoic, plants evolved alongside mammals, creating increasingly complex ecosystems. Angiosperms spread and diversified, producing fruits, nuts, and seeds that demanded specialized foraging strategies. Forests and grasslands shifted with climate cycles, forcing mammals to adapt repeatedly. These interactions reinforced evolutionary feedback loops. Plant innovations prompted mammalian adaptations, which in turn influenced plant dispersal and reproductive strategies. Intelligence, flexibility, and behavioral sophistication became increasingly advantageous traits in this dynamic system. By the late Cenozoic, one mammalian lineage had begun to demonstrate capacities beyond mere survival. Hominids, small and unassuming, developed bipedal locomotion, manipulative hands, and complex social structures. Environmental pressures, including seasonal climate oscillations, resource scarcity, and competition, shaped cognition, planning, and communication. While other species remained dominant in their ecological zones, these early humans gradually began to exert influence, not only on immediate survival, but also on the broader environment. The post-dinosaur world is a lesson in opportunity born from catastrophe. Extinctions reset ecosystems, removing dominant forms and opening space for innovation. Mammals, previously constrained by the shadow of dinosaurs, flourished through adaptability, intelligence, and ecological versatility. Arboreal primates, small predators, herbivores, and semi-aquatic forms all explored niches that were unthinkable in the Mesozoic, each experiment building the foundation for the complex biosphere of the modern era. For millions of years, evolution worked quietly but relentlessly, favoring species capable of responding to environmental instability with innovation. Climate cycles, ice ages, and vegetation shifts continued to challenge mammals, selecting for cognitive flexibility and adaptability. This slow, persistent shaping of intelligence set the stage for a species capable not merely of surviving, but of transforming the planet itself. One lineage, in the shadow of millions of others, begins to demonstrate capacities that will eventually surpass all others. Manipulation of tools, social cooperation, planning, and environmental understanding are emerging traits forged by the pressures of a dynamic post-extinction world. The ecological canvas is rich, diverse, and balanced, yet in the subtle shifts of behavior, diet, and cognition, something unprecedented begins to take root. One species will learn to alter the planet itself. Humans emerge on the stage of Earth's history not as giants of muscle or size, but as creatures of thought and manipulation. Homo sapiens, anatomically modern by around 300,000 years ago, are at first unremarkable among mammals, small, vulnerable, and limited in number. Yet within these fragile bodies resides a brain capable of abstract reasoning, planning, and the deliberate transformation of the environment. Unlike any species before, humans can envision consequences, imagine futures, and act to shape the world according to intention. For tens of thousands of years, early humans survived by hunting, gathering, and gradually mastering fire, tools, and social cooperation. Populations expand slowly, constrained by climate, predators, and available resources. But even at this stage, signs of impact are visible. Megafauna, mammoths, giant ground sloths, saber-toothed cats, begin to vanish in regions where humans spread, suggesting that predation and habitat disturbance already exert pressure on ecosystems. Humans are the first species whose survival strategies can inadvertently influence extinction beyond natural background rates. The pace of influence accelerates dramatically with the advent of agriculture around 12,000 years ago. Forests are cleared, rivers are redirected, and soils are plowed. Humans become ecosystem engineers, reshaping landscapes to meet the needs of crops and livestock. Biodiversity declines in areas under cultivation as monocultures replace complex habitats. Species unable to adapt to human-modified environments vanish, often within centuries rather than millennia. In just a few generations, human activity begins to outpace natural evolutionary and ecological processes. Industrialization, beginning in the 18th century, marks an unprecedented intensification of human impact. The discovery and use of fossil fuels, coal, oil, and natural gas, release stored carbon into the atmosphere on a global scale, altering climate far more rapidly than any natural process in recent Earth history. Temperatures rise, oceans acidify, and weather patterns shift. Forests are cleared not just for subsistence, but for mass production. Cities expand across landscapes, and transport networks crisscross continents. Energy, previously limited to direct human or animal effort, becomes concentrated and global, enabling transformation on scales unimaginable in earlier eras. Extinction rates accelerate sharply. Studies suggest that current species loss is hundreds to thousands of times higher than the background extinction rate observed throughout most of the Cenozoic. Amphibians vanish in response to habitat destruction and disease. Large mammals shrink or disappear under hunting pressure. Birds, fish, and insects decline as ecosystems fragment and climates change. Coral reefs, once resilient across multiple mass extinctions, bleach and die at unprecedented rates. These losses are no longer the result of asteroid impacts or volcanic outbursts. They are driven by conscious decisions, economic systems, and technological power wielded by a single species. This sixth extinction is fundamentally different. All previous mass extinctions were products of earthbound or cosmic forces, climate shifts, ocean chemistry disruptions, volcanism, or asteroid impacts. Nature operated without awareness, without agency. Humans are the first species to influence the biosphere with intention, foresight, and knowledge of consequences. We do not merely inhabit the Earth, We alter its chemistry, hydrology, and climate, intentionally or not. Carbon dioxide levels now exceed anything seen in the past 66 million years. Oceans are warming and acidifying, and landscapes are transformed at continental scales. Agriculture, urbanization, and fossil fuel extraction intersect with population growth to accelerate the pace of change. Forests are cleared for farmland, water is diverted to sustain cities, and chemical pollutants infiltrate soils, rivers, and oceans. Species that once thrived under stable climatic and ecological conditions are suddenly confronted with environmental pressures that exceed their adaptive capacity. Evolution, normally a slow response to gradual environmental change, cannot keep pace with the rapidity of human-driven transformation. Some species survive, but their success is often contingent on human intervention. Domesticated animals such as cows, pigs, and chickens proliferate because humans propagate and protect them. Certain pests and opportunistic species, rats, pigeons, and cockroaches, thrive in human-dominated environments. These survivors are not the result of natural selection alone. They are beneficiaries of human activity, adapting to niches created or maintained by our presence. In this way, the sixth extinction carries a signature previously absent from Earth's history: human choice, intent, and agency. The transformation of Earth by humans is not limited to land. Oceans, long buffers against terrestrial disruption, are now profoundly affected. Overfishing collapses fish populations. Plastic and chemical pollution accumulate in gyres. Rising temperatures and acidification disrupt the reproductive cycles of marine invertebrates, alter migration patterns of fish, and destabilize plankton communities that form the base of oceanic food webs. Marine extinction, once a slow process shaped by natural forces, now proceeds on timescales of decades or centuries. Climate change exemplifies the unprecedented nature of this extinction. While past events like the end Permian or end Cretaceous extinctions involved abrupt temperature swings driven by external forces, today's warming is driven by deliberate extraction and combustion of fossil carbon. Human societies accelerate these changes, often without mitigation, creating environmental stresses that are not only rapid but persistent. Unlike asteroid impacts, which are instantaneous, this is a slow-motion disaster unfolding over centuries, yet with the potential for comparable ecological consequences. The planetary consequences extend beyond species loss. Humans alter the carbon cycle, the nitrogen cycle, and hydrological systems. Forests are replaced by farmland and cities. Rivers are dammed and redirected. Soils erode at unprecedented rates. Even geological processes, once independent of biology, are affected. Sediment flows, nutrient deposition, and atmospheric composition now carry the imprint of a single species. Earth, for the first time, is a planetary system influenced consciously by its inhabitants. The paradox of the sixth extinction is stark. Intelligence, the very trait that allows humans to understand and mitigate ecological collapse, exists alongside behaviors that accelerate it. Unlike previous extinctions, which proceeded without self-awareness, this one is driven in part by conscious decisions, choices to extract, consume, and alter. The potential for both destruction and stewardship exists simultaneously. In this context, the sixth extinction is not merely an ecological phenomenon, it is philosophical, existential, and historical. It challenges the assumption that intelligence confers permanence or dominance. Dinosaurs dominated for millions of years, yet even they could not withstand sudden, catastrophic forces. Humans, despite foresight, are testing the boundaries of planetary resilience, determining whether intelligence will serve as a guardian or as an accelerant of extinction. Species decline continues across the globe. Amphibians, highly sensitive to environmental stress, disappear at alarming rates. Large mammals, constrained by habitat loss and hunting, vanish in regions where they have existed for millennia. Coral reefs, unable to recover from bleaching events, erode, eliminating habitats for countless marine species. Insects, critical for pollination and nutrient cycling, are declining, imperiling both natural and human systems. Extinction is accelerating, and its drivers are unique, conscious, cumulative, and global in scope. Humans now occupy a position in Earth's history analogous to the asteroid or Siberian traps, but with one critical difference. Unlike natural disasters, our influence carries intent and awareness. Our actions determine not only which species survive, but which ecological networks persist, how biogeochemical cycles function, and even the long-term habitability of the planet. The sixth extinction is therefore unprecedented, a convergence of biological consequence and conscious agency. The question that arises is unavoidable. Are we the cause of the sixth extinction, or are we merely witnesses to a process we cannot fully control? Every action, from deforestation to fossil fuel consumption, from industrial agriculture to urban expansion, compounds pressure on the biosphere. Yet within these same actions lie the tools for mitigation, conservation, restoration, renewable energy, and sustainable management. Humanity is both agent and observer, capable of destruction but also of stewardship. The sixth extinction is underway, but it is unlike any that preceded it. Previous events were imposed by forces beyond the perception of life itself. Asteroids, volcanism, climate shifts that unfolded over thousands to millions of years. Now, the force is conscious, deliberate, and global. Extinction is no longer random. It is a reflection of choice, culture, economy, and technological power. The trajectory of life, for the first time, rests in the hands of a single species. Are we causing or witnessing the sixth? The Earth in this moment is not simply changing, it is unraveling. The biological systems that appeared stable as recently as the mid-20th century are now collapsing at scales that rival the earliest stages of the most severe mass extinctions in deep time. Scientists across disciplines are sounding the alarm. Life on this planet is diminishing not gradually, but precipitously, and the primary force behind the decline is humanity itself. Over the past 50 years alone, monitored wildlife populations, mammals, birds, fish, reptiles, and amphibians have fallen by an average of nearly 3/4. In some regions, the numbers are even more catastrophic. Freshwater wildlife populations have dropped by more than 80%, and in Latin America and the Caribbean, the average fall in vertebrate populations approaches 95%. These figures reflect not just the disappearance of individual animals, but the collapse of ecological networks, the loss of predators, prey, and pollinators alike, and the erosion of the natural processes that once stabilized ecosystems. In parallel, global assessments of biodiversity paint an equally sobering picture. A comprehensive report compiled by hundreds of scientists from dozens of countries concludes that around 1 million animal and plant species are currently threatened with extinction, many within decades rather than centuries, an unprecedented concentration of risk in human history. Native species abundances across terrestrial habitats have declined on average by at least 20% since 1900, and major groups such as amphibians, reef-forming corals, and marine mammals are facing crisis levels of risk. These are not isolated incidents, they are global patterns. Migratory species, whose annual cycles once spanned continents and oceans, are in decline across nearly half of all monitored groups. In many cases, over 1/5 of these animals are threatened with extinction. What is driving these declines is not mystery or chance. It is a confluence of human-traced forces, habitat conversion and loss, direct exploitation of organisms, climate change, pollution, and invasive species introduced through global trade. In the hierarchy of threats identified by leading scientists, changes in land and sea use, the conversion of forests, wetlands, and grasslands into farmland, urban areas, and industrial zones top the list, shaping the fate of species far more powerfully than any other factor. Climate change, though newer in impact, is rapidly rising as an equal driver of biodiversity collapse. Insect populations, often unseen yet foundational to ecosystems, are collapsing even within protected reserves. a sign that the crisis extends beyond direct human contact. Long-term studies across Europe, the United States, and the tropics reveal declines in insect biomass so steep that entire food webs are threatened. One study documented flying insect populations dropping up to 60-fold in some regions over decades, losses so profound they have been described as half the tree of life disappearing within a human lifetime. The extinction crisis is not only about species disappearing from the wild. Populations of species that remain extant are collapsing to the point where they no longer fulfill their ecological roles. Even if a species is technically still alive somewhere, the loss of 90% of its individuals can render it ecologically extinct, functionally absent from the systems it once sustained. This phenomenon is particularly visible in freshwater ecosystems and biodiversity hotspots, where habitat fragmentation and human pressures are most intense. Scientists measure biodiversity loss against a baseline known as the background extinction rate, the pace at which species would be expected to disappear through natural evolutionary processes in the absence of catastrophic events. Historically, this rate is estimated at roughly 1 to 5 species per million species per year. By contrast, current extinction rates are now thought to be hundreds to 1,000 times higher, even when conservatively calculated across well-studied groups like mammals, birds, and amphibians. These elevated rates are what drive scientists to ask whether the planet has already entered a new mass extinction, compressing losses that would normally take millions of years into decades. Critics argue over the exact numbers or whether the midpoint of a mass extinction has been reached, but the trend of acceleration is undisputed. Extinction does not unfold linearly, it can escalate as ecological networks collapse. When one species disappears, dependent species, predators, prey, pollinators, symbionts, follow, creating cascades of loss that accelerate the breakdown of ecosystems. The result is a compounding crisis that does not slowly fade but progresses in waves of collapse. Habitat loss is the clearest example of how human systems drive extinction. More than 3/4 of the terrestrial environment and about 2/3 of the marine environment have been significantly altered by human activity. Forests, wetlands, and grasslands, the ecosystems richest in biodiversity, are being carved up for agriculture, pasture, mining, roads, and cities. Commercial demand for commodities like beef, palm oil, timber, and soybeans drives deforestation at rates far beyond the capacity of nature to recover, with wealthier nations often exporting the destruction to biodiversity hotspots in the tropics. Climate change compounds these pressures. Rising temperatures, shifting rainfall patterns, and increased frequency of extreme weather events push species beyond their physiological tolerances. Coral bleaching events, driven by warmer waters, have devastated reef ecosystems that serve as nurseries for countless marine species. On land, heat stress disrupts reproductive cycles and alters migratory patterns, and small, range-restricted species become particularly vulnerable. When climate change interacts with habitat loss and pollution, the combined effect accelerates decline far faster than any single factor acting alone. The impact of pollution, from plastics and heavy metals to agricultural runoff and industrial chemicals, is pervasive. Microplastics have been found in the deepest ocean trenches and in the bloodstreams of birds. Chemical pollutants impair reproduction, alter hormones, and reduce immunity in wildlife. Nitrogen and phosphorus runoff from agriculture create vast dead zones in coastal waters where oxygen is depleted and few organisms can survive. These chemical stresses add another layer of pressure to ecosystems already burdened by habitat and climate stressors. Invasive species introduced through global trade and travel disrupt native communities. Invasive plants can outcompete local flora. Invasive predators can decimate prey species that evolved without defenses. Once established, these non-native organisms can be nearly impossible to eradicate, and they reshape entire ecosystems in ways that reduce diversity and resilience. One of the most visible indicators of the crisis is the decline in pollinators. Butterflies in North America, for example, have declined by more than 20% in just 2 decades, largely due to pesticide use, climate change, and habitat loss. These declines have direct implications for agriculture and food security. Without pollinators, many crops would fail, threatening human sustenance as well as ecological health. While the overall number of species lost so far does not yet match the proportions seen at the peaks of the Big Five mass extinctions, the rate and continuity of loss are already comparable to the early phases of those events. And because extinction accelerates as ecosystems unravel, the trajectory matters just as much as the current tally. Patterns observed in deep time show that when rates accelerate beyond baseline for sustained periods, ecosystems are approaching tipping points from which rollback is extremely difficult. Survival patterns in this modern crisis echo those of past extinctions, but with a twist. In ancient events, species with broad ecological tolerances, high reproductive rates, and large geographic ranges were more likely to persist. Today, some of those traits still confer advantage. Generalist species, animals and plants that can live in human-modified environments, exploit a wide range of food sources, or tolerate temperature extremes, are disproportionately represented among survivors. Rats, pigeons, crows, and certain insect pests thrive in urban and agricultural landscapes. But this is not resilience in the way evolution once meant it. It is opportunism in the face of ecosystem collapse. Conversely, specialists, species with narrow habitat requirements, specific dietary needs, or limited dispersal ability, are disproportionately at risk. Amphibians, many of which depend on specific temperature and moisture conditions, are among the most threatened vertebrates today. Migratory species, whose life cycles depend on a sequence of ecosystems across great distances, are collapsing in numbers. Large mammals with slow reproductive rates struggle to maintain viable populations as habitats shrink and human conflicts escalate. These vulnerabilities reflect ancient patterns of extinction, but the cause is profoundly different. Not random cosmic or geological forces, but human economic and cultural systems that shape landscapes and climates. In past mass extinctions, life eventually rebounded over millions of years, reshaping itself around new winners. Today's crisis, compressed into decades of human activity, challenges the very foundations upon which life evolved. Extinction in the 21st century is not driven by nature alone. It is driven by a species capable of understanding extinction and its causes, yet still entangled in behaviors that accelerate it. Extinction no longer comes from nature alone. Life on Earth has endured catastrophes beyond imagining. 5 times, the planet's biological tapestry was torn, shredded, and rewoven through processes far larger than any individual species or ecosystem. Each mass extinction was indifferent to dominance, intelligence, or ingenuity. Trilobites, ammonites, giant marine reptiles, and dinosaurs all fell, not because they lacked complexity, not because they were weak, but because forces far beyond their control reshaped the world faster than they could adapt. Extinction is, in its essence, a filter applied without consciousness. And now, for the first time in the history of life, extinction faces a species that can understand it. Humans are aware of the forces they have unleashed, of the climate, deforestation, pollution, and industrial pressures that accelerate the decline of other life forms. Awareness alone does not protect against collapse, but it transforms the nature of the crisis. The 6th mass extinction is unique because it tests not merely survival or adaptation, but the capacity of intelligence itself to recognize danger and respond. All previous endings were blind. Life responded, species adapted or they perished, but there was no foresight, no moral calculus, no anticipation of consequences beyond immediate survival. Today, humanity observes the decay of coral reefs, the loss of forests, the collapse of insect populations, and the disappearance of megafauna. We can measure, predict, and project the consequences of our actions. we can trace species lost to our choices, not to the whims of a comet or the eruptions of basalt flows. For the first time, evolution is facing a conscious agent. This consciousness imposes responsibility. Extinction is no longer a distant, impersonal phenomenon. It is an ethical, scientific, and existential challenge. The survival of countless species, the stability of ecosystems, and the future of intelligence itself are entwined with the decisions humans make in the next decades. This is not merely stewardship for the sake of other species. It is stewardship for the planet that defines the conditions under which intelligence can persist. The question is stark. Will humanity become another failed experiment? The record of the past is sobering. Species vanish when ecological thresholds are crossed, when environmental change outruns adaptation. Human activity threatens to replicate these conditions on a global scale, compressing what once took thousands or millions of years into mere centuries. Without intervention, the sixth mass extinction will resemble its predecessors, sudden, total, and indifferent. The difference is that we cannot plead ignorance. We see the precipice. Yet within this crisis lies the potential for a remarkable reversal. Unlike previous mass extinctions, the sixth allows for deliberate action. We possess the knowledge to stabilize climates, to restore habitats, to protect species, and to mitigate the most destructive forces of industrial civilization. Genetic science, conservation biology, renewable energy, and global cooperation are tools unprecedented in history. These are instruments not of evolution, but of conscious intervention. Intelligence now has the power to shape survival outcomes for life itself. Responsibility, however, is neither easy nor guaranteed. The complexity of global systems, climate, biodiversity, human society, ensures that no single action is sufficient. Delays amplify losses. Feedback loops can push ecosystems past points of no return. Even well-intentioned interventions may fail if implemented too late or without coordination. Intelligence is tested not only in innovation but in foresight, patience, and restraint. It is a trial unlike any recorded in Earth's past. The sixth mass extinction also reframes the relationship between humanity and the natural world. We are not separate observers, nor merely external agents of change. Our survival is intertwined with the health of ecosystems, the abundance of species, and the stability of climate. Intelligence alone is insufficient. It must be coupled with ethical foresight and ecological literacy. The experiment is no longer about who survives, but whether conscious awareness can break the pattern of collapse that has claimed so many lineages before. History offers lessons. In every prior extinction, survivors shared traits of flexibility, small size, broad tolerance, or the ability to exploit marginal niches. Today, humans are both the largest disruptors and potentially the most capable stewards. Our choices will determine whether the patterns of the past are repeated or rewritten. Extinction is no longer a force of nature alone. It is now a mirror reflecting the consequences of intelligence. Science illuminates both danger and opportunity. Models predict that without rapid action, biodiversity losses will reach levels comparable to the greatest extinctions in Earth's history. Ecosystem services, pollination, water purification, climate regulation will collapse in many regions. Yet these same models also suggest that coordinated mitigation, restoration, and reduction of greenhouse emissions can stabilize ecosystems, allowing species to recover and life to persist in forms both familiar and new. Humanity is at a juncture where knowledge, technology, and ethical choice converge. The outcome depends on deliberate, informed action. Perhaps the most profound aspect of this moment is its reflective quality. Past extinctions occurred without awareness. They were events imposed upon life. The sixth mass extinction asks not only whether life will survive, but whether intelligence can redefine its own relationship to survival. The stakes are unprecedented: the potential loss of countless species, the destabilization of global systems, and the challenge to the persistence of intelligence itself. And yet, this also offers a unique possibility, the first recorded instance in Earth's history where an intelligent species may consciously prevent or slow a mass extinction. In the quiet of reflection, one realizes that survival is no longer accidental. It will be measured by foresight, humility, and collective action. Intelligence is no longer merely a tool for domination or exploitation. It is the mechanism by which extinction may be averted. The test is whether humanity can rise to the responsibility it has created, not simply to persist individually, but to maintain the conditions under which life in its diversity can continue. The sixth mass extinction is not inevitable, but neither is it avoided by default. Every choice, from energy systems to conservation strategies, from agriculture to urban planning, shapes the trajectory of life. Unlike the asteroid that ended the Cretaceous or the Siberian traps that suffocated the Permian, this crisis is conscious, participatory, and morally freighted. Extinction is no longer a blind force. It is now a question of ethics, knowledge, and deliberate action. The Earth has survived 5 endings. The 6th will decide what intelligence truly means. If this journey through our past helped you understand what it takes to survive, subscribe to Science of Survival. We release new documentaries every week, exploring extinction, adaptation, and the fragile line that keeps humanity alive.